Okay, we'll talk in this part or class about, let's continue as a follow-up of the rates, uh, the reaction, and we just explain the zero order reaction. And in this one, we will talk about first order reaction or equation, and um, let's write whatever we already know earlier. As an example, we have amount A and we have amount B. If we are talking about the rate of decrease in A, which is similar in kinetic or pharmacokinetics to the elimination rate. Okay, so let's write the differential equation that will represent this reaction. dA over dt will be equal minus K multiplied to A to the power of 1. Okay, this is rate of change in amount of A over change in time. So it's rate of decrease in the amount of A. Okay, this is because we are talking negative, because we are talking about decrease in A. This is will be, as we are talking about first order, called first order rate constant, and this will be the amount of A at time t. Okay, so just if we just rewrite it, amount changing the amount of A over time equals minus K multiplied to the A as the amount. So it's again differential equation that define or represent first order kinetic or first order reaction. Okay, this is the rate. The unit will be, if you're talking about mass of A, mass over time, this will be mass as unit, and this will be accordingly, which is important, what? 1 over time, or, okay, reciprocal time. Okay, this is very important. So the rate would have mass over time unit, the constant will have 1 over time unit, and the amount will have mass unit, as we know. Okay, if we are talking about definition or what affects what in the first order reaction, we can see that in here, if we just take this, I will just rewrite it here, dA over dt equals, okay, we know, again, this is rate, this is constant, first order constant, and this is amount. Okay, so if we are just looking to this equation, we can find that the rate is proportionally related or directly related to the amount of the drug remained at time t. Okay, or at certain time, because we are talking about certain time here. Okay, it's not constant as in zero order. So one the rate if we are talking about first order, not constant. For sure, this is one of the differences. For sure, K, which is first order, constant, rate constant, is for sure is constant. Okay? Again, the constant unit is 1 over time, not as mass over time. And the rate is not constant, but at the same time, it's dependent proportionally. We are talking about the rate here, okay? Proportionally related to the amount remaining in the first place or in the body at time t. Okay? Those are the main difference so far. Okay, let's continue. If we are talking back or just go back to the differential equation that we have. For again, just to remind ourselves, we are talking about first order reaction will be multiplied to A. Okay, so again, this is differential equation and we need to deal with it. And to deal with it, we need to have similar terms at the same side of the equation. So we will rearrange the equation to have 1 over A, right, multiplied to dt equals minus k multiplied to, sorry, dA multiplied to dt. Okay, okay. So again, it's differential equation and we need to integrate from 0 to time t. This will give us 1 over time dt will give us ln A from 0 till time t. Constant will go out, multiplied to time from 0 to time. Okay? If we substitute whatever that we have, ln amount of time t minus ln at initial amount equals minus k multiplied to the time at time t minus 0. So again, this will be ln minus k multiplied to the time. If we just have this as our y, so we need just to um, remove this to the other side of the equation. So it will be ln A at certain time equals ln A naught minus k multiplied to the time. So this will be one of the first equation that represent zero order reaction in ln term. Okay? If we are talking about whatever that we have in this equation, we know that this is amount of the drug, let's say, or the material at time t. Okay, this is the initial amount that we have or the amount that we have at time 0. This would be first order rate constant, and this is the time that we are talking about in here. Okay, so this is the first equation to represent or show the first order reaction. Okay, we can have it in different terms and I'll show you this in a minute. Okay, so just to rewrite, okay, this is our first equation. It's in the ln term. I want to have it in a log term. Can I have it in a log term? Remember that to change ln to log, I need to divide by the number that we usually use, and I told you it's very important. It's 2.303. So if we divide the whole equation, then will be log a at certain time, right? Then log a naught, which is the initial amount, minus k over 2.303 multiplied to the time. Okay, so this will be the second way to represent the first order reaction. Or we can just use this equation and rearrange it by having ln A at certain time, which was like this, right? So ln one term minus ln the other term, we could have it in this way, right? Ln A at time t minus ln A naught. So it will be minus. Okay, to just get rid of the ln, we need to take the exponential or the exponent of this. Then we will just get rid of that. So A at certain time over A naught will be the exponent to the power of minus k multiplied to the time. Okay, if I need to have this as y, then A at certain time equal A naught minus multiplied to the exponent of or e to the power of minus k t. Okay, this is the last equation that we can represent the first order reaction using it. And again, this is in the ln term, this is in the log term, and this is an exponential term. If we are talking about type of equation, this is linear, equation, and this is exponent equation. Okay, so, and again, those are using terms of A as amount of the drug, and as I just mentioned in the zero order reaction, we can have it in terms of concentration of the drug by just knowing that the concentration of the drug equals amount over volume. So I can just divide the amount by the volume of the drug to have the concentration. So each and every equation that we have, 1, 2, and 3, we can have it in terms of concentration at a certain time and initial concentration by just dividing the amount over the volume if we are talking about volume that is not changing over time. Okay, so can we draw those kind of equation? We will start by each one of them and just be focused and concentrate with me because this is very important for you in this course. Okay, so let's start with the first one, which is the ln A at certain time equals ln A naught minus k multiplied to the time. We mentioned that this is linear equation, okay? Again, it's the same as y equal ax plus b, right? And if we remember, this is our slope and this is our constant, right? Which is y-intercept. So if we are drawing ln A at certain time versus this, then accordingly I will have this as my y-intercept and this as slope. Okay, so let's try to draw it. we will have positive intercept, which will be equal to ln A naught, and it will be decreasing because we have negative slope, right? And the slope will be equal to what? Minus k. So from this equation, we were able to determine ln A naught, in which we can determine by having anti-ln, the initial amount of the drug, and we can determine from the slope k, which is the rate constant, first order rate constant. Okay, and this is on rectilinear graph, and again, remember this is linear equation. What we draw here, if you have data, we have time, we have amount at certain time, and then we took ln A at certain time. So what we did here, I took the ln for each amount that is here in this column. And what we draw here in the graph, we have this as our x, and we have this as our y. Okay, let's continue. The other equation, which is the equation of the log term, or in the log term. Okay, if we are talking about the log term, let's write it again. It will be log A at certain time equal log A naught minus K over 2.303 multiplied to the time. One important thing that you need to keep in mind, don't forget about this number. This would affect your calculation so much if you just forget about it. So it's very important to remember it all the time. Okay? Again, I want to draw this as my y and this as my x. On rectilinear graph or linear graph, I will have log A at certain time versus time. If I have it as it was in the ln term, this is our y-intercept, right? And this is the whole thing. Let me just remove that to be easier for you to follow me. So I will just have it everything. Okay, so log A at certain at initial minus k over 2.303 multiplied to the time. Okay, so again, this will be our y-intercept, and the whole thing, which is the coefficient on t, will be our slope. So again, I have negative slope, so it will be decreasing, and this will be the y-intercept, which is log A naught, and the slope will be equal to minus k over 2.303. So again, from this equation, which is in log term, and again remember it's rectilinear, I was able to determine log A naught, which is the y-intercept, and from anti-log I can determine A naught. Another thing, from the slope, which is equal to minus k over 2.303, I will be able to determine by multiplying those terms k, which is the first order rate constant. Okay, And again, if we do the same thing and see what we had here as data, we will have time, which is our x, and we have a at certain time, and then we have log a at certain time. So I took the log for each and every amount that I have at different time points. Then to draw, we have this as y terms and this as x terms. Okay? And the same thing would be if we are talking about concentration terms. It will be just log concentration, if it's concentration, by multiplying the amount over volume, dividing the amount over volume. It will be log concentration, which is C naught minus K over 2.3 or 3 multiplied to the time. Okay? So the last equation that we have, which is the exponent equation or the exponential equation, and this will be explained in a second. Okay, so let's write it again as we just did, minus k over time. Okay, again, amount at certain time, initial amount for time of time 0, first order rate constant, and the time that we are talking about. If I want to draw this as my y and this as my x, what is your drawing or sketch will be? So this is amount at certain time and this is the time. And again, don't forget that we are talking about exponential term. Okay? As we are talking about exponential term, then we will have exponent profile or exponential profile related to this term. And one more important thing that we have minus here. So it will be a decay or a decreasing exponential profile. So if we want to draw this profile, it will be okay. So it will be exponentially decreasing, and if we either you'll have it as at time equals 0, or by extrapolation you will have what we call it the y-intercept, okay, which will be equal to a node, and we can't use the slope here because we have exponential graph. So you can do that as we were using for the previous two equation, because this is exponential equation. Okay, so this is will be on rectilinear graph or linear graph. What if I changed this to, again, before we change this, I have here time and a at certain time. We didn't change anything. We just have it and draw it here on the y-axis. Okay. What if I changed the graph rather than rectilinear to simulog graph? Okay. So this is simulog graph. I'm just changing the scale of the axes, or I'm changing the graph or the paper I'm drawing on. So this is semi log graph. We have here a at certain time versus time. So the scale of this axis changing to the log scale. Okay, the profile that we will have is like this for the first order reaction, in which we have here as a node. What we are drawing here, if we compare it to this, is time and a time. So we are just drawing the same thing here. We didn't change anything. We are drawing the same terms, the same numbers, okay? We are just visualizing it differently on a log scale. So we are not doing any actual log transformation here as before in the equation number 2. We are not doing any log transformation. It's just changing the scale of the y-axis to the log term. So we will have units here for sure for the amount, and we will have units here also for the amount, because we are just drawing the same thing, but we are just changing the profile that we are, the graph that we are drawing the profile on. Okay, so, and the same thing, this equation would be the same in the concentration term, but we are just dividing the amount by the volume. This would be concentration at certain time equals concentration initial minus K over time. Okay, so the last point that we need to mention for the first order reaction is the half-life. Okay, for the half-life, again, as we mentioned earlier, we know that the time that is needed for the amount of the drug or the concentration of the drug to decrease by 1/2. Okay, so if we take any of the equations before, any of them, you can take it as, again, if we write all of them here, okay, you can use any of them to have the half-life of the action. So let's do it with the ln, for example. So we have ln a at certain time. I will just have this on the same at the same side, and then this equal minus k multiplied to the time. Okay, I need to have a at certain time according to the half-life definition. So at half-life, at the half-life, we will have a at certain time equals half the initial amount, right? So let's substitute this. So a ln half the a initial amount minus ln initial amount equals minus k multiplied to the half-life, right? So we just change this to the initial half of the initial amount, and we just change this by substituting the time with the half-life. Okay, so len minus len would be len half a naught over a naught, right? Equals minus k multiplied to the half-life. To get rid of the len, we need to take the exponent of the term, okay? So if you are taking the exponent of the term, you will have half-life, okay? Take the len of the both sides, you will have, and for sure if you use the exponent equation, it will be shorter for you, but the same thing. Every pathway you will use would be the same, okay? So this would be length the half, which would be equal minus k multiplied to the half-life. Okay, so just keep the half-life at one side only. This would be point minus 0.693, which is this, over k. Okay, if we just remind ourselves with what is this, sorry, if we remind ourselves with what is this, we know that this is the half-life of first order reaction. Okay, this is the first order rate constant with the unit of 1 over time. Okay, and this is for sure number, so it's constant. So we can know from this equation, and by the way, you'll have the same equation of the half-life first order reaction, whatever the equation that you are using to just have this final equation for the half-life. And we can know from here that the time required for the amount to decrease by 1/2 or the half-life of first order reaction is constant. And this is another important difference between first order and zero order. So, which means if we are having, I will just draw the mono-exponential term that we profile that we already have for a first order reaction, okay, on rectilinear graph. We know, or we just mentioned, that it would be this, right? So if we said that this would be our A node, okay? So A node at, let's say, this time, it would be half A node, right? Because it's what we are talking about the half-life. So this is would be the half-life, which let's say, for example, is 10 hours. If we are talking, and this is, let's say, 100 milligram, and this is 50 milligram. If we are taking another half-life, which is 10 hours, okay, this would be half this amount, which is 25 milligram, half its initial, okay? And the same thing, so on and so forth. So the half-life of zero order reaction is constant. Please don't forget that for first order reaction. Okay, that's it. And we will stop here. Then we will start with the IV bolus model next time.